This is the Neurodynamics lecture series, lecture 6, part 1. A quick rehearsal. Last time we talked about stability in 2D. For that we introduced two coupled differential equations that describe the change of x, here x dot, and the change of y, here y dot. We did a linear approximation near the equilibrium based on the reasoning that first the null lines separate the space into different parts. Inside each of the different parts the behavior is the same, and secondly, mathematically we can actually show that if we have higher order terms, the higher order terms do not contribute if we are close to the equilibrium, because x squared goes faster to 0 than x. So the only remaining terms near the equilibrium are the linear terms. This allowed us then to write the coupled differential equation as x dot equals a times x plus b times y, and y dot as c times x plus d times y. So we have only four parameters, a, b, c, and d, which we can write in a matrix form to illustrate the very same differential equation. That means we have now a vector of x dot and y dot. We have a matrix composed of a, b, c, and d, which is called the Jacobian, and we have the state of the system, that is x and y. We then realize that the Jacobian is describing the full behavior of the differential equation. And we also realized that instead of looking at the Jacobian itself, it's sufficient to look in its eigendirections. This is depicted here for the saddle node on the lower right side. The eigendirections are the directions which describe the principal behavior of the system, which are these two lines. Mathematically speaking, these are the lines in which the direction is not changing. So with other words, if we start the dot somewhere here in the center and we follow in the eigendirection, then the ball is only rolling in this eigendirection and not going in any other direction. So that means we can decompose the behavior of any possible direction, of any possible trajectory, into the two eigendirections, which are the principal behaviors. So to find these principal directions, we realize that this is actually the eigenvector, and the corresponding eigenvalue tells us whether the system is contracting, so whether it's actually going towards the fixed point or whether it's repelling. We then realize if it's only about determining whether the solution is stable or not, it's sufficient to look at the eigenvalues only, because the eigenvalues tell us whether in a certain eigendirection the system is attractive or repelling. So without knowing the directions, the knowledge of the eigenvalues is therefore sufficient to identify stability. To get the eigenvalues, we can actually solve the characteristic equation, which is the determinant of the Jacobian minus the identity matrix multiplied with minus lambda, which gives us the characteristic form, which looks like this, the characteristic polynomial. And if we multiply that out, we can actually rewrite it this way, defining the constants tau that compose all the parts that are scaling linearly with lambda, and all the parts that actually are independent of lambda, which we lump up in delta. We then realize that that tau is a trace of the Jacobian, which is a plus d, and delta is the determinant, which is a times d minus c times b. Once we had this, we could actually solve the characteristic equation for lambda, and for that we know we have two solutions, and we can plug that into the PQ formula, and we get the very similar solutions. The only difference is that we have a different sign here. So if the value under the square root, which we can see here, is positive, then we get actually two real valued solutions, lambda 1 and lambda 2. If the value under the square root is negative, then the square root will be imaginary. Since we are then having two solutions that has one positive imaginary part and one negative imaginary part, we know that lambda 1 and lambda 2 are so-called complex conjugate solutions. So that means lambda 1 and lambda 2 have then the very same real value, but they have the imaginary part with opposite signs. We then actually characterize the different solutions, and the first thing we did is we looked for the solutions that were completely real. That means that actually the value under the square root was positive. In this sense, we have a demarcation line here that separates the positive part under the square root from the negative part. So everything outside this parabol is actually positive and therefore real valued. Everything inside is complex valued. Then the second separation was that we also separated in terms of a repelling or attractive structure, and we then identified two principal solutions. The first is an unstable focus, which we find here. So that's a system that is repelling out, but it's repelling in this periodic fashion towards the outside. Or we have a stable focus. That means we have a system that attracts the states, and therefore it's a stable it's a stable fixed point, but it's not in a linear fashion. It's actually in this periodic fashion that it's attracting it, so it's circling in. So these are the parts that have a complex solution. Everything outside of this has a pure real valued solution, and then there are only two cases. One with a stable node. In this case, it's attractive in both principal directions, which we have in the yellow region, and the other two parts are unstable fixed points, because at least one of the two is repelling. In this case, actually both are repelling. As you can see, these are the two principal directions. Both are repelling, and here this is a saddle node. This is actually attractive in one direction and repelling in the other direction, which is sufficient for an overall unstable condition. We then actually characterize this again as a summary. So if we do the eigenvalues and they are both real and of the same sign, then the node is stable when the eigenvalues are negative and unstable when they're positive. If we have both eigenvalues real and of opposite sign, then this implies that one is attractive and one is repelling. Overall, the system is repelling as well, and therefore unstable. We also can have stable and unstable foci. This happens if the eigenvalues are complex conjugate, and they are stable when the eigenvalues have negative real parts, and unstable when the eigenvalues have positive real parts. With that, we are coming to bistability, or oscillatory two-dimensional system, as one of the principal solutions that you will find in spiking behavior of neurons. Before we dive into this, I would like to remind you on one very important property. If you plot a phase plane, and this phase plane is characterizing the activity of a two-dimensional system, and you're doing, as here, a two-dimensional representation, then actually the trajectories of a system should never cross. Or more generally speaking, if you look at trajectories of an n-dimensional system and you analyze that in an n-dimensional phase plane, then they should never cross. Why is that? Well, if they would cross, so for example, if you would have, and keep in mind this is impossible, a situation like this and the one that is depicted here, in this very spot where they are crossing, you wouldn't know how to continue, which is impossible because the differential equation defines for every single point a single solution or a single change. So that would mean this is purely impossible. So that means whenever you see something like this in your analysis or in your plotting, this must be wrong. It can only happen if you have, let's say, a three-dimensional system and you're plotting it in 2 dimensions, because in plotting it in 3 dimensions is difficult. Then it could happen that the third dimension is disambiguating the two. But for every point in the phase plane, if you are doing it in an n-dimensional system with an n-dimensional analysis, you have to have a unique direction how the system continues, and that implies never ever have any crossing trajectories like here. Okay. Before we come to periodic activity, we should actually formally introduce what that implies. A trajectory that forms a closed loop is called a periodic orbit or periodic trajectory or limit cycle. All these terms you will find in textbooks. And this just implies that you have a system that has some kind closed loop, closed orbit or limit cycle, that if the system is on this limit cycle, it will continue its very same behavior forever. So it will circle around, it will spin on this. And that essentially implies that you have periodicity, and you can actually very easily define periodicity simply by this equation here, saying that if you observe 2 points, x and y, then after a certain period that we call t, we have the very same points again. So which means we are here, and a time t later we are exactly at the same point, and this holds for any other point, so we can actually do this here also. After a certain period t, we are again at the very same point t. So since this holds for all parts of the trajectory, and t is the period length, that is a periodicity, we know that actually the system is staying on a periodic forever repeating circle. If we now talk about stability, then we also need to talk about stability for these 2-dimensional systems like the limit cycle. We just simply extend what we actually learned for a fixed point. For a fixed point, we said that a fixed point is stable, that eventually the system is ending up in that fixed point if we wait long enough. And eventually means if we wait for t going to infinity, the system is exactly on this fixed point. We can do the very same thing for an attractor that is not a fixed point but a limit cycle. Here we just then assume that the system is approaching the limit cycle, and if we wait long enough, which means t goes to infinity, we are exactly on the limit cycle. That means if we start here, we are approaching from the inside and spiraling out until we get very, very close, and if we wait long enough, we get actually infinitely close to the limit cycle, which means we are on it. That means the attractor is attracting the states from the inside. That also means immediately that if the attractor states the limit cycle attracts all states from the inside, there must be something like an unstable fixed point in the center. Because only if there is an unstable fixed point in the center, the states are repelled away from the center towards the outside. So it does not really have to be exactly in the center, but there must be an unstable limit cycle somewhere inside the limit cycle. You can also just look at this from a topological point of view. Then actually a stable limit cycle in an energy potential would be corresponding to something like an inverse donut. So you have essentially, if you do the projection from the side, you have valleys like this, and you have a mountain like this, and then the system is spiraling inside this topology. So it's essentially like a donut that you rotate by 180 degrees. If the limit cycle is unstable, the very same thing happens like for a fixed point. An unstable limit cycle doesn't mean anything else that if you are exactly on the limit cycle and you're subject to a very, very small, infinitely many small perturbation due to noise, then you will be repelled to the outside or the inside. And the distance between the future states and the limit cycle will grow over time. So that means they are repelled away. Again, this implies that in the middle of an unstable limit cycle there must be a stable fixed point, because the distance is increasing as a function of time. That essentially means that at some point they have to converge to a central point in the middle. Okay. The next thing we will do is we will talk about bistable systems and apply the knowledge that we learned so far. Before we come to that, I would like to rehearse quickly what actually is going to happen in a one-dimensional system. In a one-dimensional system, two stable equilibria are always separated by an unstable equilibrium and vice versa. This was just the case because if we have f of v, which is the change of the differential equation, as you remember, and we are looking for fixed points, and f of v have to be, the change have to be 0 at the fixed point. And the slope at this very same point determined whether we have a positiveness, which means that we have an unstable fixed point, and a negative slope, which is a stable fixed point. So that means if you have many zero crossings and you just have a one-dimensional system, then in between a positive and another positive slope there must be a negative slope, because otherwise you cannot actually put a continuous line in this. And we always assume that we have differential and smooth behavior, so that means as a consequence of that we can only have alternations of positive slope, negative slope, positive slope, negative slope, which essentially means that in between of like two stable equilibria there must be always an unstable one. For more dimensional systems this is actually not anymore the case. Nonlinear two-dimensional systems, for example, can have many coexisting attractors. And you see here one of these examples on the right hand side. This is actually a Fitch-Nagumo model that has two stable equilibria separated by an unstable one. So red highlighted are here the two stable ones, and there is this unstable one in between. Such system is called bistable or multistable when there are more than two attractors, because the system can either be on the left side or it can be on the right side. And if it's there, it stays there. So for the Fitch-Nagumo model, that would mean you can have dynamics that are associated with the left-hand side, and that is a resting potential, or you are on the right-hand side, and that then is essentially associated with periodic spiking. So that essentially means, depending on the initial condition, so whether you are on the left or the right-hand side, you are staying in these two domains. So from a one-dimensional system, we would actually expect that these two domains are separated by an equilibrium, right? And that's actually what we did when we showed that we have a certain fixed point, right? A single point that is separating the two. Here, this is different. It's actually not separated by a single point. It's actually separated by a line. And this is the so-called separatrix. The separatrix separates the yellow space that is the attraction domain of the stable fixed point on the right-hand side from the white area that is the attraction domain from the fixed point on the left-hand side. So if you are initiating a system anywhere in the yellow part, it will actually go to this fixed point. If you have an initial point on the left-hand side, it will approach the stable fixed point on the left-hand side. So in neural models, this bistability results from the coexistence of an equilibrium attractor corresponding to the rest state, left, and for example a limit cycle or an attractor that is on the right-hand side. Usually we have on the right-hand side a limit cycle that essentially means that we have a system that would undergo repetitive firing. So that means we have a neuron that can either be at rest if it's on the left-hand side, or it can be on the right and then it's actually firing in a periodic fashion. So in a one-dimensional system, this unstable fixed point was the separation point between the two stable fixed points as we introduced in one of the very first slides. So what's the role of this unstable fixed point here? Because we now know it's actually not the point at all, it's actually the separatrix as a line that is separating the two. Well, even though we know it's not sufficient, it still plays an important role because it's anchoring the separatrix. At this very point, the separatrix is actually initiated, and then from there on, it's going into two principal directions if it's a nonlinear system in a curved fashion. In very many cases, this unstable fixed point then that is actually forming this separatrix is a saddle node. A saddle node that is repelling in one principal direction that you see here, and that is attracting in the other principal direction that is this one. So with other words, the attraction direction, the principal direction that is attracting, is the anchoring line for the separatrix, while the repelling direction is the direction that defines the principal behavior once you cross this anchoring line. So similar to an unstable manifold of a saddle, it's formed by the two trajectories that originate exactly from the saddle. The unstable manifold is parallel to the eigenvector corresponding to the positive unstable eigenvalue, which is the blue one, the repelling one, and the stable manifold of the saddle plays the role of the threshold, since it's separating the resting state and the spiking state. So we can actually have a close look at just this very close environment surrounding this unstable saddle node. So the first thing we do is we identify the principal directions: red attractive, blue repelling. We can now discuss from 4 different initial points, and we start here with A. So if we start in A, we are in the yellow region and we are attracted to the right side, and finally ending up either on a stable fixed point or on a stable limit cycle. In B, we are repelled away from this manifold, and since this is in the whitish area, we repel towards the resting state. Only if we stay exactly on the separatrix, we feel no repelling force in terms of either going to right or red, and we would essentially stay on the line that is directly approaching the limit cycle. So with other words, in the very same point close to the saddle node, we have the principal directions, which is a line because we approximated the Jacobian with a linear approximation. Of course, we know that this is actually not the full solution, so we can't really describe the behavior that is far away from the saddle node with a linear approximation. And therefore, the separatrix is curved. This is the linear part that we had been ignoring to define the principal direction in the very close proximity. So now we have the methods to really discuss a real neuron that has this bistable behavior, and we are using here the INAP plus K model that we had been introducing before. As you can see here, we have a slightly different yellow region than the one that we actually saw in the Fitsunakumo. The reason is that here I selected one that has actually a periodic limit cycle inside this yellowish region. The whitish region is a region that is associated with the resting potential. So that means wherever you start in the white region, you will get back to rest. Even if you are here on the right hand side, you would essentially follow a trajectory that goes like this. Inside, you have a stable limit cycle, which means wherever you start, you end up eventually on this limit cycle. And inside this limit cycle, you have, of course, an unstable fixed point that we discussed already. The separatrix is the anchoring point that's actually separating the yellow from the green, and for that, very close to the fixed point, the unstable fixed point, we can actually compute its eigendirections. We have the repelling eigendirections here, and along the attracting eigendirections, which is these eigendirections, along the attracting eigendirections, we have the anchoring of the separatrix. If we get far away, we get a curved shape because the Jacobian is, of course, only describing the behavior correctly, very close, with the leading terms being linear. Okay, so that means if we study this principal behavior, this neuron is actually a very specific neuron, because usually we would assume that a neuron is first at the resting potential, right? So the neuron is sitting here. So what happens if the neuron gets input? Well, if the neuron gets input, it can be positive input, so excitatory input. So the neuron would actually see a slight deflection and would go to the right hand side. The membrane potential would increase. Well, it also could be inhibitory, right? So what the neuron would do then, it actually would return very fast back to the resting potential. So if it's here, it would essentially return back, and if it's here after the stimulus, it would return back in this direction. During this process, if the activity is not very strong and very quick, the slow variable will also change. So for example, if we are here and we apply a very strong voltage perturbation, as a consequence of that, the slow variable may change, right? That means that we might, if the stimulus is strong enough, cross the threshold either here, or we cross this threshold either here. And as you can see here, depending on the value of the slow variable, whether the slow variable is 0.05 or whether the slow variable is 0.0, we have a different kind of threshold, right? Because the separatrix is defining the membrane potential at which we're transition from the left hand to the right hand side. Even more extreme it would be if the neuron would be subject to a rather slow and long-lasting input, which would allow the neuron to accumulate a calcium or an activation of the slow variable n for a long time. So in this case, the threshold would be much different. It would be actually something like minus 40 millivolts, while the threshold, if it comes directly from the resting potential, would be close to more minus 60 millivolt. And this is why I had been emphasizing so much there is not a single threshold. The threshold depends on the exact way the neuron is excited. Is it exciting slowly? Is it exciting fast? Is it excited with a very strong impulse? Is it excited with very small impulses? Or if there is maybe some kind of still remaining potential remaining activation of the slow variable, because the neuron is returning from essentially a previous firing state. Nevertheless, this is important. It's important to realize that the threshold depends on the exact way that the neuron is subject to an input. Number two, irrespective where this threshold is crossed, if it's crossed here, or 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 even if it's crossed here. If it's crossed, then the activity is contained from that time on inside this yellowish period, because the neuron produces the exact same pattern again. Again and again. So that means we have a bistable neuron that either sits at rest, and once it is excited, it keeps firing forever. Only if the system with a certain additional drive would be pushed leftward, it would stop firing. So if it's on the limit cycle, then at several points we could make the neuron stop firing. For example, if it's here and we apply an inhibitory input and we push it across the separate tracks to the left hand side, we would make it stop firing. Or, and that might be surprising to some of you, if it's here and it's actually in the upstroke, if you give it another strong input, then we would actually push it outside the yellow as well, and the system would return to resting potential. So that means we can, if it's here somewhere in this range, we can actually push it with a positive input out of the yellowish area and make it silent. Or if it's on the left hand side of the N-null line, we can actually do it with an inhibitory response. So as you can see, there are several ways to actually get a system spiking or to silence it. And to characterize this, we use a characteristic of the way that actually it's approaching a limit cycle. And for that, we introduce the homoclinic and heteroclinic orbits. We say a trajectory is heteroclinic if it originates at one equilibrium and terminates at another one, which you can see here. So it starts in one, here on the right hand side, and ends in another one. A trajectory, in contrast, is homoclinic if it originates and terminates at the very same equilibrium. So here you see it starts here and it terminates here. These points, however, are very rare. The reason for that is that you have to have a very specific geometry, that if it's approaching from here, it's actually turning rightwards and not leftwards, and you have a fixed point in between. Keep that in mind. So homoclinic orbits are very rare. Both types, however, play an important role to understand actually the dynamics of a system, and especially excitability. And we will use these in the next lecture to characterize the principal behavior in terms of information integration. Heteroclinic trajectories connect essentially unstable and stable equilibrium, and they are ubiquitous in dynamical systems having two or more equilibrium points. Homoclinic orbits are rare. First, a homoclinic trajectory diverges from an equilibrium, and therefore the equilibrium must be unstable, right? And second, the trajectory makes a loop and returns to the very same equilibrium. It needs to hit the unstable equilibrium precisely, since a small error would make it deviate from the unstable equilibrium and therefore turn into a different direction. So both together then makes the homoclinic trajectory very rare to happen.